So I'm an assistant professor at UNC Chapel Hill, and when I talk to people about what we do in my lab, I tell them that we're working as scientists and engineers as well. So our research is really in the field of task-based optics. So we take inspiration from the field of photonics, microscopy systems, fancy cameras, of course, fancy optical, electro-optical devices, and we combine that along with light sculpting techniques. We combine that with computer sciences, and this is where my background is. I'm originally a computational imaging person, so at the interface between computer science and optics, where the combination of good hardware and good software can give rise to advanced imaging systems. And in my lab, to distinguish myself from what my past advisors are doing, is I apply this to everything else you can do use light beyond imaging, and specifically using light, applying those technologies and those techniques to use light in an efficient way to interact with living specimens. So in particular, in the area of neurosciences, where we have some tools at our disposition, optogenetics, where you can use light to activate or silence neurons, and calcium imaging, voltage imaging, where you can use light to pick up fluorescence that encodes functional information about your neurons and try to collect that information. So in theory, we have all those beautiful tools to read and write the brain, but we need technologies that basically best leverages those fantastic tools and best serve the neuroscience community and the neuroscientists that are trying to make sense of those signals. So one of the recent highlights of what I've been up to a couple of years ago when I was finishing my postdoc is we developed a technique called 3D shot. Bruno has been talking a little bit about how this technique is made commercially available and providing plenty of help to set up the technology in anybody's lab. The core idea of this technology is basically to use holography to activate neurons. And so this is basically a highlight of how it works. The diagram you see here shows you basically a schematic of what temporal focusing is. The idea is that you take a femtosecond laser, it sends you short pulses, you break the pulse into colors on the diffraction grating, and then you let each of the color constructively interfere in the image plane, matching the diffraction grating, and you create what is called a temporally focused spot. And that temporally focused spot is something that has been, over the years, identified to be perhaps the best way to stimulate a neuron, because it creates this uniform, constrained illumination pattern where in the vicinity of the temporally focused, there is 2-photon absorption that is possible, and around it, not, which means that you create a spot that specifically addresses one neuron. So we create a temporally focused spot, and then we holographically, using a special light modulator, replicate a P of this temporally focused spot in multiple locations at once. That's what the essence of 3D shot is. The core technology that is basically driving on the software side 3D and other techniques that aim to place light in neurons is a computer-generated holography technique that basically takes input from the user to decide where to place the light, and then generates this 3-dimensional object that places the light and the right amount of light on the neurons you want to target. And so this is what this talk is going to be about today. Is about basically developing the algorithm that allow you to do experiments a little bit like this one. Here, what you see is basically a calcium imaging live, and simultaneously, wherever you see the little arrows, a 3-dimensional hologram that places light at a different frequency to activate optogenetically custom neural ensembles. So this is one example that we've been able to obtain in our 2018 Nature Neuroscience paper. And where my lab is working right now is enabling this type of application to be done in real time with really minimal delays. And so this is the outline for today's talk. So what I'm going to do is dial back a little bit from the very basics of holography, and I'm going to go as fast or as slow as possible on this, and then I'll introduce computer-generated holography techniques. I'll discuss a little bit some of the tools that I put on GitHub to basically give an introduction on those techniques, an introduction to Fourier optics, and basically follow you through using those algorithms. And then I'll talk about different types of CGH algorithms, some that are fast, some that are efficient, and then we'll talk about how deep learning really enables to get something both fast and efficient in the application that we're targeting. And then in the rest of the time I have, assuming that I don't flag for going over time, we'll talk a little bit about like what I feel really excited about, which is basically like pushing forward the envelope of what can be done, one photon techniques that are particularly popular in the audience that we have here today, which, you know, really sees value in two photon techniques that can go deep in the brain. So I'm going to show you some of the recent results we've had and why perhaps this is something that we should not be like pulling away from the table of discussion right now. So by all means, you know, this is a small audience. I welcome interruptions. What I'm going to try to do is keep the chat box active, or I'm also going to keep monitoring actually, it's a small audience. Feel free to interrupt me as needed for questions. I've put the links to the code that I'm going to show you on GitHub. If you want to follow along, you can download it, open a MATLAB tab, and run it with me. So to get started, I'm going to go back to all the way to like wave optics. So what do we mean with wave optics? It's a model where we represent light as an electromagnetic wave, and we try to predict what it does. So the simplest model we really know is the model of the point source, a single oscillation, perturbation of electromagnetic field that we characterize basically with a wave amplitude. Typically, we talk about the electric field, but we talk about this as like the amplitude of the wave, and we just ignore what it means. And its angular frequency, omega. And so the one thing we know about point sources is we know express the wave period, the wave frequency, the angular frequency, but also we know how to predict how it gets over time. So if we take a certain distance r, we can express the state of oscillation at a distance r from the point source as a simple phase delay, e to the I kr, where k is 2 pi over lambda, the wave vector, that basically expresses the delay of the oscillation that is acquired as the wave oscillates from as the wave propagates from its source to the place where it's observed. That's all we know about the point source. One of the few models that we know how to explicitly like define. We ignore some of those things like attenuate, but I'm going to talk about that later on this way. The beauty of the wave optics model is that so equations are linear differential equations. What that means, one of the consequences of that is that if you find two solutions to the wave propagation equation, the sum and linear combinations is also a solution. So for instance, what that lets us do is basically solve problems like this one, where here we have two apertures that could be treated like point sources, and we'd like to express, for instance, the state of the field at a certain location. So if I take one source and one point source, I can express that the field perceived in B by a source right here is the state of oscillation at the source in red, modulated by the delay e to the I kr. And if I now have another source in the field right here, I can basically consider another point source and say that the field that I observe in B will be the sum of the contributions of the two linear differential equation. Look at that. And that basically gives me the ability to calculate an explicit solution and basically express the state of the intensity where as the function of like where I'm located, and find basically the state of intensity depends on the location of the screen, where sometimes the interferences are constructive, sometimes they are destructive. So this is an illustrative example, and in general, the Huygens-Fresnel principle generalizes that to a complex field that is basically like defined across a wide area. So the way to implement that is you carefully select the contour with no source inside. You identify boundary conditions. You say that you're going to basically, you happen to know what the state of oscillation is everywhere here around the boundary. So for instance, 0 everywhere here, and like established across this space here. You treat each point on the boundary like a point source for which you know the state of the amplitude and the local oscillation. And what linear superposition tells you is that you can treat each point like a point source. And if you want to calculate the state of oscillation somewhere inside this volume, all you need to do is treat each point like a source, add the resistive delay induced by the distance from the source to the point where you measure the state of oscillation, and add the contributions of each of the point sources. And if you do that sum, calculate that sum, you'll be able to find what the wave looks like at this location. And you can repeat this operation over and over to basically populate your entire volume and compute the state of the field in the entire volume. So this looks a little bit complicated, but basically you can express that as a convolution product. So here in this Fresnel propagation wave equation, you basically express that if you happen to know the 2D phase and intensity in a particular plane, so for instance in z equals 0, you can predict the state of the oscillation in the rest of the 3D volume simply by integrating the contributions of all the points in the 2D plane that you happen to know very well, treat those as point source, associate to each point source the delay induced by propagation from the point source to the point where you calculate the field. And by calculating this convolution operation, you can predict the complete field everywhere in the space. And so we have written that as a nice like propagation function. A convolution operation is calculated in the Fourier domain for the purpose of like simplifying this is calculated. But we basically develop a simple MATLAB code where if you specify the complex field, for instance, field 1 at z equals 0, associate to it a wavelength, define a certain propagation density z, and specify the dimensions of your space by specifying the point spread, the pixel size or the spacing between your sampling points in the x and y axis, you can basically calculate the propagated field and complex field. So I have a simple MATLAB code that can do that. So here, if you download the stuff we have on GitHub and you look at the day-one wave propagation, we have an example field where we take an image. This is the UNC logo. We assign to it certain wavelengths, a certain pixel size, certain dimensions of the field, and we simply propagate the field at a certain distance. So here we do it iteratively. And if you run that code, you can basically visualize how light propagates as a function of distance. This is basically running right here. And for instance, after 10 centimeter, you can find that the amplitude, the intensity looks like that and basically simulate the effects of wave propagation. There's nothing much more to it. The take-home story is that if you happen to know the phase and the amplitude of a complex wave in a particular plane, you can easily predict what happens to that wave at a certain distance. So this is basically a forward model, and it has an explicit operation. So this is just a link to the simulations if you want to get the link and run it for yourself. Another thing that we've done in Fourier optics is to simulate the propagation of light through a thin lens. So here, instead of looking at locally what happened to the lens, we choose to simulate an FF system. So this is a particular optical system where you take a thin lens, a focal length f, and on either side, you consider yourself at a distance f from either side. So your input field here is A of x, and your output field here is B of u, the output field at distance f. The reason why we pick this particular configuration is that it's actually easy to calculate. You can basically apply the Huygens Fresnel and say that the state of oscillation here at coordinate u is the sum of the contribution of every point on the x-axis treated like a point source. And if you write that up using the delay here, dl, as a function of x, u, and f, you can express the Huygens Fresnel propagation and say that the field in u is the sum of the contribution of oscillations along the x-axis treated like point sources and modulated by a delay that depends on x here. And if you write this equation, what you find is that what you're calculating here is actually nothing else but a Fourier transform, where you specify the k vector, the k axis of your Fourier transform as a function of u and f, the focal length of the lens. Actually, I think it's u over f square. I'll have to check that. Anyway, the bottom line is that what we find is that an FF system, so basically a lens with a piece of free space of dimensions f on either side, performs what is called an optical Fourier transform between this axis here and that axis over there. So we simulated that as well. So we basically wrote a MATLAB function that does this operation. We specify the input field, complex field. we specify the pixel size along the X and Y axis, the focal length f that you use, and the wavelengths. And the output of this function is the complex field on the other side of those. And for sampling reasons, the pixel size that the Fourier transform assigns to it, which is not the same pixel size as the input field. This allows you to have the input field and the output field to contain exactly the same amount of points, and basically gives you a way to visualize what happens to the field as it passes through an optical system. So one of the applications we have in the simulations that we have here is a simple imaging system. So for instance, here I have an input field, so Mr. Fourier. This is the intensity distribution. If I pass Mr. Fourier through an f term at this axis, what I will look at is this intensity distribution. And for the purpose of my simulation, for instance, I choose to occlude the field to simulate what happens when the field passes through, for instance, a pinhole aperture. So if I apply a 0 to all the rest of the light here that is above a certain spatial range, my field restricts to these dimensions. And if I run in this field through an FF system, I can reconstruct the output field. Oops, sorry about that. And in this example simulates basically what the resolution limit is in an optical system, where if you run through a certain pinhole aperture, the output field has a limited spatial resolution. Because it's limited in a spatial frequency domain, you basically apply a low pass filter. You can visualize here the limited resolution. So here with MATLAB, you can just simply run the simulation that we have here. That's basically simulation number 5, where you start with an input image. You assign to it a certain size by specifying the pixel size and its dimensions. And you apply function length twice. You modulate the field in the Fourier domain by applying a mask that zero everything except for around the aperture. And if you run that code, this is basically what you can simulate, where the input field is this nice contrasted image. At the FF system, this is what you observe. If you crop the field to simulate an aperture and you only keep this part, this is what you see after you pass through the lens. Now, to give you an example of what the simulation looks like, I'm going to simply change the size of the aperture. So if I make the aperture, let's say, like 3 times as big, this is what happens when I run the optimization, the simulation. Now I have an aperture size that is 3 times bigger, and you can see that my resolution in the image plane has significantly improved. So we have other simulation tools here. One of them, for instance, like simply simulates what the PSF or the simple microscope model can look like. You can run that. I'm not going to go too much into details in that part because I want to move on to other things I want to show you. But basically, with these 2 simple tools, you have a complete Fourier toolbox, which is what I like. If you have a custom optical systems with a bunch of lenses at custom locations, you can very simply simulate in a Fourier model of wave propagation what happens when you propagate an input field from an input phase to an output phase. All you have to do is simply apply the function length to go through FF systems and use propagation, even in a reverse way, to go from place to place. So for instance, with these 2 lens systems, I do an FF system from here to there. I do a reverse propagation to go all the way to here. And then I can go again through an FF system to go all the way to the output field. So by combining the lens operation, which is a Fourier transform, and the Fourier propagation that brings you from one plane to another through free space, you can basically simulate Fourier propagation waves through custom optical systems. So very, very simple toolbox if you want to see what happens through an optical system. And something you can easily like fit with apertures and other things that are really simple to model in the optics. So what do we do with that? Well, let's go to computer-generated holography. Our goal is to create custom illumination patterns. And we do so typically with a coherent light source, a laser beam that we nicely expand and collimate to create a wave. And in the typical Fourier, the typical implementation of holographic systems, what we do is we modulate the wave with a special light modulator. So a special light modulator is this device with liquid crystal assigned to each pixel. And at the local pixel level, what you can do is apply a voltage that's going to change the configuration state of your liquid crystal. And what it does is that it applies a little delay to each pixel, and each delay can modulate the phase, typically between 0 and a little bit more than 2 pi. So what you can do is, with a computer, assign a voltage to each pixel, and then pixel by pixel, apply a simple wave modulation to your incoming wave. And so we modulate the wave with a special light modulator, and we let the wave propagate through an optical system, typical FF system. And then at the output of the optical system, we would like to generate a custom illumination pattern. And the whole idea of computer-generated holography is, if you happen to know what pattern you want to create in the image plane, calculate what would be the best way to modulate the wave at the SLM plane to obtain the illumination pattern that you want to create. And so that happens to be an inverse problem. In the Fourier propagation, in the forward propagation model, the things we've discussed just before, everything is fine. Once you know the phase and the amplitude in one plane, you can calculate what happens in the rest of the volume. Here we have an inverse problem, because we happen to know in the SLM plane, we happen to know the amplitude. It's what the laser provides us. We can measure it. We can put a camera right there, and we can observe the amplitude, but we don't know the phase. This is what we need to calculate. Oppositely, if we go to the image plane, in the image plane, we have an intensity distribution that is very well specified. It's what we want to create, but we don't know what the phase will be, and we don't have particular constraints on what it should be. So we have basically constraints at two different levels along our propagation axis, but at no point do we have access to both phase and amplitude. So the problem is not fully determined. We have to solve this as an inverse problem. So there are examples of, first, perhaps the simplest example of optimization technique that can address this problem is the Gershber-Saxton optimization. So how does this work? We start from the image plane and we say, well, this is what we want our intensity distribution to look like. We know the intensity, we know the amplitude, but we don't know the phase. So the whole idea of Gershber-Saxton, if you don't happen to have access to information, just start with something random or arbitrary. So we assign to our field a phase. That is definitely not the right answer, but it's all we have. We just put a phase, 0, random, whatever you want it to be. And now we start at the plane of the image plane. We have an amplitude that is defined by what we want it to be. We assign a random phase, so we now have a complex field. If we have a complex field, we can use the tools that we just discussed. So we take this complex field and we propagate the field back to the plane of the SLM. At the plane of the SLM, the complex field we have has an amplitude and a phase. The phase, so far, is our best guess for what we should be putting on the SLM. But the amplitude is probably not what we have. The amplitude probably doesn't match what the laser gives us. So here what we're going to do is simply keep the phase, but replace the amplitude with the specified amplitude at the laser at the SLM, the amplitude at the SLM that the laser gives us, typically a uniform or a Gaussian pattern. And we're going to update our complex field with what would be a best guess, a better guess for what the amplitude looks like. So now we have a new amplitude, a new phase, we have a new complex field, we can propagate it forward. And by propagating forward, we go back to the image plane, where the amplitude that we get is what our best guess for rendering would be. But perhaps will not match what we want it to be. So this step, we will again replace the amplitude by what we want it to be. We enforce another amplitude constraint in the image plane, and we assign to it the amplitude. So this process can be repeated, and basically by going back and forth between the SLM plane and the image plane, at each step we keep the phase, but we update the amplitude to be either what we want or what we know is true, and we recycle over and over. And if we look at the rendered field, this is basically what things look like as the number of iteration and the computation time increases. On the diagram right here, we measure the accuracy, so basically a measure of match between the target and the rendered hologram. When it's equal to 1, we have a best match. Here we basically see that as we increase the number of iteration and the computation time, the accuracy increases. And this is basically what the Gershberg-Saxton algorithm does. After a large number of optimization, our accuracy becomes pretty good. This is what the render field looks like. And if we stop the cycle right here, the output after k iterations gives us here what our best guess is on what should be put on the SLM to create a hologram. So this is the earliest 1972 Gershberg-Saxton algorithm that allows us to compute what a best case of what the phase should be to create the hologram. Now, this is called iterative exploration because I call that cooking. It's an algorithm that basically tries to enforce constraints and oscillates between two planes, and eventually basically happens to converge where we don't really know why, nor do we have a guarantee that it will converge. It just happens to work. And this is what the simplicity of this algorithm. So if you go back to MATLAB, and if you go to the Gershberg-Saxton holography code that we have, you can see, if you scroll down, there's a lot of code that corresponds to basically displaying what happens in real time. But you can see that the core of the algorithm is this loop iteration across the cycles, where we propagate the field forward, we update the amplitude in one plane, and then we propagate the field backwards, and then we update the amplitude in the other plane. And if we do that over and over and over, we can basically run the code. So there are a few lines here that correspond to the code. Everything else is about displaying the results. And if you show the results here, you can basically see the computation of the hologram in real time. You can measure the residual error, which is like similar to the accuracy. And you can basically visualize what the hologram will look like and what the phase pattern looks like. And you can see here that the phase domain is basically like a very, very interesting, intricate pattern that when applied to the SLM will render the hologram that we have here. And you can see that the hologram is, of course, slightly imperfect, doesn't match exactly what the target intensity looks like. But that's basically what you can get with Gershberg-Saxton, an extremely, extremely simple algorithm to implement. So that's what the state of the art was for holographic synthesis back when I started my PhD, and I worked a lot on this. And one of the first things we did is, like, computation starts becoming slightly inexpensive. We say, can we come up with better holograms than this algorithm? And so 2017, we developed this algorithm that treats the holographic computation as an optimization problem. Here's what we do. We say that we have a special light modulator that can apply a phase modulation phi of xy. If we know the amplitude and the phase, we can propagate using the tools that we discussed before. We can propagate the complex field we create into the 3D volume and render a three-dimensional illumination pattern I of xyz. Now, the holography problem says that, this basically says that we have a linear forward simulation that, given a phase, gives us an intensity distribution in 3D. Now, when we want to make holograms, we specify a volumetric distribution that tells us where we want the light to be. And the holography problem as an optimization problem is to say, if I create a cost function, h, that measures the mismatch between v, the hologram I want to create, and I, the hologram that I can synthesize, the hologram I want, the optimal phase, is the phase that minimizes the cost or the mismatch between v, the intensity distribution I want, and f of phi, the intensity distribution that will be rendered when the phase phi is applied on the SLM. And so that optimization problem here is a differentiable function, which is great, but it's a non-convex problem and it's a multivariate problem. So it's extremely difficult to solve. The primary problem is that it's a non-convex optimization problem. And so when a problem is non-convex, finding solutions using techniques like gradient descent doesn't guarantee that you'll find the optimal solution. If you apply gradient descent, you're likely to fall into a valley and find a local minima. And this is basically what we did. We just tried gradient descent optimization and say, well, what happens when we do that? And so even though the algorithm that we developed to solve this optimization problem only has the capacity to find local minima, we found that it's actually able to better explore the space of possible holograms and find solutions that are better than what Gershberg-Saxton can give you. So this is a summary of the technique. So we write the optimization problem, and we solve this optimization problem with gradient descent techniques. And what we find is that if you're willing to wait even more time, because the problem is actually even more greedy computationally, you will be able to find solutions that are even more accurate than what Gershberg-Saxton can give you. So if you think about it, Gershberg-Saxton is this like line right here. And the reason we're able to publish our work is that we are able to push the envelope a little bit further and given more computation time, basically like compute holograms that are actually slightly better and slightly more matched to what we want to create. So this was the state of the technique back then. We are very excited about this technique because H is a cost function that we can pick however we want it to be. So for instance, we at the time when I developed this algorithm with my colleague Jing Zhao, we basically thought about applying it to multiphoton holography. And we say, well, in multiphoton holography, I don't try to match an intensity distribution. I know that my multiphoton response is going to be proportional not to the intensity, but to the square of the intensity. So what we did is we say, well, we can actually just put that into the optimization directly and optimize the hologram not for a match of the intensity distribution, but for a match of the desired two-photon excitation profile. And we did that. And what we found is that we were able to compute holograms that were able to combine very well the excitation patterns that we could create. So this is a map of the two-photon excitation response with our technique and with iterative algorithms and comparison. And so we're very excited by that. The other thing that I started looking into was basically optimizing the CGH problem for application in optogenetics. So in optogenetics, for instance, we have a bunch of neurons genetically targeted neurons that are labeled with an opsin, and all the neurons in the volume that we're targeting, that we were able to infect with a microbial opsin, express an optogenetic opsin that makes them sensitive to light. So in bulk optogenetics, you put a fiber, eliminate all the neurons, you can turn them on, you can turn them off. But what the lab I was in at the time was starting to look at is like functionally defined subpopulations of neurons that happen to be genetically identical. So you can label that population with optogenetic modulators. But what we're interested in doing now is, can we target subtypes of neurons within that population of neurons that happen to express the opsin? So in this example, for instance, I show you a volume, and all the neurons that you see express the opsin, but I basically pick in red random subpopulation of neurons that I'm interested in targeting. And in blue, you see a bunch of neurons that happen to express the opsin, so they're sensitive to light. But in that specific task right here, I would like to not eliminate them. So if you compute a hologram with Gershberg-Saxton or with an algorithm that has a uniform cost function, the illumination profile that we use here in Bordeaux labels, the illumination will equally penalize light that lands anywhere that is not the neurons that we want to target. But if you look at the red neurons, it's not a suitable illumination pattern. What we're trying to do here is a clear violation of Maxwell equation. We want to place light in neurons, and we don't specify how the light should get there. And if you think about it, putting light into neurons, the light has to come in from somewhere. In fact, like in other words, you cannot have energy deposited in neurons without having the light coming and come out of it. The hologram, the intensity distribution that I'm trying to target here, the red neurons, is not a suitable solution to Maxwell equation. It violates energy conservation principles. And so I know that, and the intensity distribution I target is my best guess of where I want the light to go. But if I use a uniform cost function to that, there will be stray light. The stray light is needed to bring the light towards the target. And that stray light may hit some of the neurons in blue and inadvertently stimulate the neurons I'm trying to like stay away from. And that's a problem that needs to be addressed. So we can address it by basically like identifying how the light should propagate there. But the better solution that we have is basically to modify the cost function, relax the constraint about any light that is like in the empty space between the labeled neurons, but put a hefty penalty for any light that happens to land in the neurons that at this time we're trying to avoid. And this is the kind of like hologram that we can create when we optimize the neuron, the cost function for a neural photoactivation task. And what you see here is a hologram that, if you look at it in 3D, basically doesn't look anywhere near what we specified as the target intensity distribution. But if you look at how much light lands in the targets and how much light lands in the targets we're trying to avoid, has a much better contrast and perform the task we're trying to perform much better than holograms that are computed with iterative techniques or without specifying anything in the cost function. So this made a case for basically customizing the cost function and tailoring the cost function to the task and to any priors you can include into the model. For instance, the fact that we know that we're optimizing for the 2-photon response. So that's basically the name of the game. So we're trying to like use those holographic techniques to place light in neurons and in application like this, where we try to read and write into neurons. But what you see here is that the techniques that we propose, like CGH, is pretty slow. It takes a second to compute the hologram in that example. In general, it's very, very slow, and it's even slower if you ask for high-resolution holograms. And so what you look at on the left here is an example application where we're doing calcium imaging and at the same time photostimulation of neurons. And time is of the essence, because talking to neuroscientists, many of them are in the room right here, neuroscientists are interested in being able to communicate with the brain. And communication is like a conversation. If I take an hour to answer your question, you will probably be thinking about something else. And my answer may not have the same effect on you than if I'm able to answer your question right away. And the same happens in the brain. The brain is evolving through states. And sometimes it is of interest to be able to modulate neural activity in direct response to what are the most recently observed patterns of neural activity. And so as a result, if you look at this diagram that compares computation time and accuracy of hologram, we want to be somewhere here in this envelope. Like the envelope is basically the level of performance we can acquire. Everything below this envelope is something we know how to make, but we really want to make holograms right here, where the computation time is kept slow because we want to be able to like interact with living systems. And the computation time stays high, and the quality of the hologram remains high because we want our holograms to place the light where we need it to be. And so we need to basically push this envelope. And the question that we try to answer is, can we push it with algorithms? The most exciting techniques that we're starting looking into was deep learning, because a deep learning technique, a neural network, is a mathematical object that operates without iterations in fixed cost. A neural network takes an input and gives you, after a series of calculations and without iterations, an output. And so the earliest thing that we thought about doing was to say, like, can we use a neural network to compute holograms? And so the idea would be like, we would specify as input the illumination pattern we want, and we would like to know if a neural network can calculate an output, the phase pattern to place on the SLM, and render the hologram we want. And so that actually was just being published in 2018. And this is basically a technique that requires supervised training, where to configure the neural network and train the neural network to perform this task, you need to provide pairs of inputs and outputs that are matched to each other. The problem of this approach is that providing pairs of input outputs is really difficult, because if I give you a particular input illumination pattern, I do not know what is the best output yet. Even with the techniques we discussed before, I'm not sure that I have found the best possible hologram. And even if you give me days to calculate it, I'm not sure that I'll be able to find the best hologram. Another thing you could do is simply like create a bunch of random phase pattern on the SLM and simulate what they look like, and use that as a pair of matched input and outputs. The problem is that you would train the neural network on randomized illumination patterns that are not relevant to the type of application you have. So this is what supervised training is. You specify random SLM planes, you propagate them, you match them to random looking corresponding intensity patterns, and you use that training data set to train the neural network. The problem here is illustrated here is that the number of possible holograms is extremely large, but the type of hologram we're trying to synthesize is actually a very, very tiny subset here. And the training that this technique would propose would not specifically train for the subset of relevant hologram we're trying to create. So my wonderful grad student Haas developed a technique that addresses that using neural networks, but with an unsupervised training technique. The first thing we did was to say, let's use the CNN wisely. A convolutional neural network works best when the input and the output share spatial features. They look similar. If you try to use a CNN to create Fourier holography, the pattern on the SLN doesn't have special properties. This is one of the clear properties of like Fourier optics, is that Fourier transform doesn't contain special information, it contains angular information. So here what we say to say, let's use the CNN to predict not the phase at the SLN, but to predict what a suitable complex field is in the image plane. Predict phase and the amplitude in the image plane that best match a suitable hologram. But now that we have phase and amplitude, we can simply, in one step, backpropagate, reverse propagate the complex field all the way to the SLN and extract the phase at the SLN. So this two-step method, without iterations, would get from the input to the output we want in a very reasonable computational time using a CNN that can compute things pretty fast. Now, how do we train the CNN to do that? Well, we take the phase at the SLN and we simulate the forward propagation for this specific phase and for the laser amplitude, and we compute what the hologram looks like when we apply this phase on the SLM using a forward model. And here, we can compare the rendered hologram to our target hologram using a loss function. And because every step of the way along this loop is differentiable with respect to the parameters of the CNN, we can use gradient descent techniques to optimize the CNN parameters and train the CNN to perform what we want. So that type of technique is called unsupervised learning. The reason it's unsupervised is that I don't need to provide ground truths. I don't need to identify pairs of inputs and outputs that are matched. I don't need to have exact solution of the CGH problem. I can just use a bunch of inputs and following the strategies here and using the red path to train the CNN, use a large data set and train the CNN to perform this task. So two advantages. First, I can use data sets and training data sets that are application specific. I can train the CNN to make holograms of blobs or holograms of cats, depending on what we're looking at. And of course, you retain the same things we discussed about customizing the loss function. You can customize the loss function to optimize the CNN to compute holograms that best perform specific tasks. So that technique is called DeepCGH. We published it in Optics Express in 2020. And so this is how the things perform.
Nico, can I ask a quick question about so you know there's two strategies that you could use here for sort of taking advantage of this mapping between the SLM phase and the complex field at the sample, right? Let's say if your CNN is like a UNet, I actually don't know what it is. Is it like a UNet?
It's a custom CNN that is based on the UNet model. I think I gotta say I'm the last generation that like went through grad school without having deep learning in their curriculum, and the expert on that is my grad student. And so I don't want to say anything too bad. It is a modified version of a UNet.
Okay,
the structure,
so I mean let's keep it simple, right? So you can either like. So it seems like you do the sort of the UNet thing in the spatial domain, right? And then do the Fourier transform. The other option might be to do the UNet thing in the Fourier domain, right?
Yeah, so absolutely.
So basically learn the phase mask and describe, you know, on a multi-scale level, the Fourier transform. Is there a reason, did you try the other thing? Is there a reason why you opted to do it in the spatial domain rather than the Fourier domain?
So we have not actually, and this is really an interesting like a discussion. I mean we should definitely explore that. My main suggestion here it was to like test that, and then it had to work early on, and we just didn't explore the other option. But I think what you're suggesting is a great idea, and I'll run it by Haas.
Well, I say this sort of greedily because we did the UNet thing in the Fourier domain, but we haven't tried your thing. And so I feel like we've tried the two sides.
Wait, did you publish that?
There's an archive paper on our method. So we were basically learning phase masks for doing activity imaging in zebrafish.
Oh, that's all right. I probably run into it. I don't know.
I'll send you the paper.
Wait, how recent is that?
Last year on archive. Yeah.
Oh, I should have run that. I'm so sorry. It should have been on my radar.
No,
but it's actually very interesting. So like it makes perfect sense to me. I think like you would be using the CNN for exactly what you say, like the input and the output have to share some spatial feature. So I'm guessing you start from the target, you reverse Fourier transform it regardless of what the application of the phase is, and then you basically map this phase to what a better guess for the phase should be using a CNN, and you train in real. So from my perspective, the outcome should be perhaps better, perhaps lower, depending on what strategy works best. And the question becomes, are CNNs better at processing sparse images because we're dealing with sparse holograms, or are they better at processing like rather uniformly defined fields? And the two together should basically tell us like which one works best. I don't have the answer, but probably we should compare techniques, and that sounds very relevant.
Yeah. So those are all the same thoughts are going through my head. So
no, absolutely. I'm happy to talk offline about that, because that sounds like an easy, like, let's work together and compare the two methods.
But something something that to speak against, using the Fourier domain is that you don't have the type of statistics that is optimal for the convolutions, right? It seems that you have a very, how to say, discontinuous, right, structure. You don't have the typical smoothness with some precise boundary, more or less boundaries.
Andrea, I'm gonna actually mitigate that, because one of the things that you see with phase is that there is phase wrapping that we're visualized. We always define the phase between 0 and 2 pi, and the reason being that we have to wrap the phase. I think that if you neglect phase wrapping, you could potentially make this work. And then you basically would have to wrap the phase when you send it to the SLM.
Phase wrapping, you mean the fact that there is this interruption in the cycle?
From the perspective of the SLM, if you take a phase function and you reduce it to 0 to 2 pi by like including by periodically like bringing back to 0 to 2 pi, in the Fourier wave propagation model will remain the same. And so, like, I think that plays into like arguing that Casper's solution is probably a good idea too, because and probably what we think about the phase domain is constrained by our vision of wrapped phase domain. But if we don't wrap the phase, probably a CNN model has equal capabilities in like rendering those holograms.
Yeah,
that's my guess.
And you absolutely can't wrap the phase, or I mean, there's a differentiability problem if you wrap the phase. And so, Nico, it's very insightful. We solve it in the unwrapped space and then wrap afterwards.
That's my guess. Yeah. Now, so do you have your code? I think we should like do a brief comparison and like and run it side by side. It sounds very exciting. Let's talk that.
This is not really by me. I'll post the paper in the chat. But sorry, please continue. Yeah.
Absolutely, no, but I'll look into it. It sounds very exciting. So I love this idea. I mean, anything coming out of Caspar's lab is, of course, something exciting. So sorry, Caspar, I should have been very familiar with your paper, and this is on me, that one. All right, so all right, let's move on. So this is basically what the model is, and so like you can see here a side-by-side comparison on like the same type of hologram. So here what we did is like a 512 by 512 sampling of the space across 7 planes equally spaced. So that's a 3-dimensional hologram. This is what Gershberg-Saxton gives you. This is what CGH, the iterative optimization with gradient descent, gives you. Iterative methods. In comparison, the computation time is like dramatically reduced with DeepCGH. What we found and what we're very excited about is that like we happen to see a configuration here where DeepCGH was actually able to obtain even better accuracy than our iterative optimization algorithm. And so what we think is happening is that because DeepCGH is optimized on a large population of potential holograms, it actually learns how to make holograms and doesn't specifically learn how to make one particular hologram. So perhaps this is indicative that when we run iterative optimization with gradient descent, clearly we land early on in a local minimum. but perhaps DeepCGH is by scrambling through large populations of training data sets, able to somehow identify solutions that are a better optimum than what iterative optimization does. So that's where we were here. So what you can see here as well is that, of course, we can consider training the same model for different hologram size. So if you make a hologram bigger with like more pixels in the XY domain and more planes, of course, the computation and time takes a hit. The other thing that we observe is that the overall accuracy drops. And I'm going to talk about that specific aspects later on. But what you see here is that basically, like even with a bigger model, the accuracy drops, the computation time is increased because the model size scales up, and the computation time really scales with the model size. I don't have that data shown here, but what you can do is you can actually tune the size of the model and adjust it to target a specific computation time, knowing that if you have a bigger model, the accuracy should be overall better than if you have a smaller model. And so the reason why we're really excited about that is that the type of time scale that we're looking at is typically within the response time of optogenetic encoders. So that means that basically our technique kind of like basically perform at speeds that at least are on the same time scales as the type of like simulation times that we're looking at. So the reason why we're excited also because of the accuracy is greater is something that Casper is very familiar with, is the issue of heat in two-photon optogenetics. And so here what we show you is on the right, our experimental setups. We have an SLM, we create a three-dimensional hologram. We use a two-photon, a femtosecond laser. And under the objective of our movable objective microscope, we create a hologram in a fluorescent calibration slide. We cut off the IR and we visualize the fluorescence, which is basically a quantitative measure of the amount of two-photon absorption that happens. And then our substage microscope moves up and down to scan across the three-dimensional hologram. We record the data and we can basically look at the two-photon excitation as a function of X, Y, Z. And so what we're looking at right here is 3 holograms that we recorded by placing on the SM 3 results for the same three-dimensional distribution of neurons, but computed with iterative algorithm like Saxton, with iterative optimization like CGH, and with DeepCGH. And what you can see is with a very same amount of laser power, that because the accuracy of our DeepCGH holograms is greater, in experiment, what that translates to is that we waste less light. There's less stray light that doesn't towards the target. And more light towards target means more intensity, means more square of the intensity, means more two-photon excitation. So why this result is important is that getting intense femtosecond lasers is not so much of a trouble. You can get 100 watts now commercially, no problem. The problem, the limiting factor, is that you cannot inject 100 watts into the mouse brain without cooking the brain. A significant study has been done. I think like the 2 main labs that have done that is Casper's lab and Valentin Emelini's lab in France. Done 2 papers on the issue of like brain heating and how much does infrared light heats up the brain. And the bottom line is that two-photon excitation techniques, especially for holographic optogenetics, are currently limited by the amount of light we can inject into the brain. So having an algorithm that gives us a great accuracy is important, because that means that for the same amount of light, the same amount of heat that you're going to be depositing in the brain, you can actually have either greater two-photon absorption, or you can distribute the same amount of light across more neurons and activate them. So that result was pretty exciting for us, because it says that using the right algorithm can afford to target more neurons for the same amount of laser power.
Nico, can you unpack a little bit why DeepCGH is getting better solutions than CGH? So
the true answer is we don't know. The true answer is there. So with, actually, I don't have any slide to show you about that, but let me roll what I think is happening. Clearly, when we developed, clearly Gershberg-Saxton basically comes up with a solution, but it's clearly not the optimal solution. And we don't have a proof that it is. But the same applies to CGH. When you run CGH optimization, you formulate the holographic problem very well. You say, I'm looking for that phase. The problem is that we apply gradient descent to a non-convex problem. And so when you run non-convex optimization, yes, your algorithm converges. Yes, it will converge towards a local minimum. And statistically, and the reason why we've been able to publish that paper in 2017, that local minima happens to beat Gershberg-Saxton quite systematically and gives us a hologram that has better quality. And so the problem that remains at this time is that, is this solution the best solution? And the answer is probably not. And we didn't know about whether this answer was legit or not until we were able to develop DeepCGH and found that it happened to work better. Initially, we're just developing DeepCGH for speed, and then in simulation, it came out that like we're able to actually get better accuracy. And so what we think is happening is this: is that when NovoCGH optimizes and finds a local minima, we're satisfied by a solution that has substantial benefits over Gershberg-Saxton. But among all the local minima that our non-convex optimization function has, it is probable, but we never were able to really find them, that there are better solutions to the CGH problems that have yet to be discovered. And so when we develop DeepCGH with a neural network that has to be trained on a very large population of neurons, the DeepCGH model learns how to make hologram. And it's a black box model. I don't have a reason to tell you whether it's going to perform better or worse. And in fact, there are configurations where if the plane spacing is not properly adjusted, a DeepCGH did not converge to better solution with CGH. So it's still like an open-ended question. And I'm sure you've experienced the same kind of trouble in generating your holograms. But the idea is that in that black box model, by going through a large population of testing samples and training data sets, we teach the CNN to identify phase and amplitude pairs that somehow are more representative of a suitable hologram. And so basically, what I'm thinking is that the space of solutions we explore allows DeepCGH to identify solutions that within all these local minima are perhaps better than what NovoCGH was able to identify. But again, I don't have a clear reason, nor like a statistical reason to, or a theoretical reason to believe that this is indeed the case. It just happens to like perform better than NovoCGH. So what it's clear is that NovoCGH clearly lands into a local minimum, and that of those local minimum, we're definitely not hitting the best. We have no guarantees we're hitting the best, and like with what we're seeing from DeepCGH, that we're not getting the best. But again, like DeepCGH is probably not hitting the best solution either. It probably is significantly better. I'm starting to believe that there's not much more improvement to be gained, and so this is why I'm making a case that like the deep learning based holographic technique seems to be like a very good compromise between speed and accuracy. They're providing amazing results. So you're in the game with that. There's the group of Jun Tanida that has been developing that original paper that is in the game. Our lab has been developing deep learning techniques. And then I think the other name that I can think of is the lab of Gordon Weinstein at Stanford, that's exploring those techniques for holographic display applications. And so altogether, what we're looking at is basically saying that like teams like deep learning is really the right type of tool for holographic techniques. And this is kind of the case I was hoping to make today on that line.
Yeah, there's a lot of this stuff going on undercover in industry as well.
Absolutely,
yeah. Facebook and Google have all sorts of cool algorithms that I hear rumors about. And one last question, sorry, super quick.
I'll go for it.
Does DeepCGH know about the constraints of light propagation, or do you have to sort of impose then, do you have to like clip? So because it generates a complex field, right, at whatever in the image plane, that once you propagate it back to the pupil, you know, you have an amplitude pattern and NA constraints and stuff like that. Is that taken into account by DeepCGH, or do you have to do some cleanup afterwards?
No, so what we do is we specify, we understand that the intensity is a constraint, and that scaling up the intensity at the SLM level will scale up the intensity in the three-dimensional hologram. So we uniformize our intensity. We say we're expecting a unitary intensity across all planes.
Yeah.
And then when we go back to the SLM plane, we just assign that intensity and we propagate it. But we use...
But there's other things, right? Like, you know, like the sort of the distribution of intensity across frequencies in the in the image plane is defined by the, if you have a phase-only hologram, it's defined by the amplitude at the pupil, right? So does DeepCGH complied with those constraints, or do you have to sort of like, do you deal with that separately?
We don't specify them. We just, no, we don't specify any of those constraints. We just basically assign, when we do the forward propagation, we assign an intensity distribution to the SLM, and it can be whatever you want it to be. We forward propagate, and then we just simply look at what the hologram, what under Fourier propagation we get in the image plane. And we just compare that to our target illumination. So at no point do we specify in the CNN model any of these intensity constraints. I think it's, I don't know if you have a technique to do that from your perspective, but if this was a refinement to our model, I'll be very interested in exploring that.
My intuition is that it's not that important, especially given your results. I was just curious. Yeah. I have to dig a little deeper into your paper, which I will.
All right.
So yeah.
All right. Well, I'll do my homework as well and read yours. Yeah. All right. So moving on. So on GitHub, I can showcase that very briefly. On GitHub, I have we have developed two things. So we have, let me just show you right here. On GitHub, we have so this is the GitHub repository for the lab. We have DeepCGH right here, so all the source code is available here. But what Haas developed, which is really practical, is a Google Colab script. And we really owe that to like the group of Andrea and the previous mnemonic conference, where Andrea had like Kaiman run on one of these like wonderful like scripts.
I don't want to take this kind of credits for Google Colab.
I was amazed by how like convenient it is. So what we have here is an example test case. We have a pre-trained model that's available, and you can basically run through like one step of optimization, and then you can simply like run the model and like and visualize like what it does and compare it. So they're basically like the type of code that we used for the paper. So you can basically simply run that and like start from a clean model of DeepCGH. If you want to like customize it for your needs, you can start from there and then tailor all the model for your needs. So we've been in talks with a couple groups at Berkeley and Genelia that have been like exploring the utilization of like DeepCGH, and so we're always happy to like troubleshoot any problems you experience to like make that available for the broader community. So if you are trying DeepCGH, if you are experiencing problems, just talk to us and we'll open a conversation. But that's really like all I had to show. So the last thing I wanted to show you is this problem that we're facing. And Spencer, how much time do you have left?
Sorry, I don't have this. Oh, here it is. Next one starts at noon, so like 18 minutes.
Oh, perfect. All right. So in the 18 minutes I have left, I'm going to leave some time for questions. But what I want to show you is this: is that what we observe when we're generating a hologram is that the more planes you specify in 3D, the lower the accuracy was starting to go. And then it's something that's very understandable from our perspective, because we are basically asking for the impossible. We are specifying three-dimensional intensity distribution in 3D. And the more constraints we put in the three-dimensional domain, the less likely that the hologram we're looking at is feasible. And on the other side, as we said before, phase and amplitude in the 2D domain, they fully determine what intensity distribution we're going to create. So in other words, even a three-dimensional holography problem is, in spirit, something that is only being addressed currently with two-dimensional solutions. We specify the amplitude distribution and the phase distribution at the SLM if we want to. But in the end, what we're generating is a two-dimensional distribution that happens to take place in a three-dimensional world. So there's a dimensional discrepancy between the hologram we want to create and the number of levers that we're able to push. And so because of that, we believe that like holography with coherent light is inherently limited. Another way to look at it is to look at what a coherent wave looks like. The wavefront that you create only allows you to have one ray direction at each spatial location. The ray direction in the ray model of wave optics, the ray is orthogonal to the wavefront. The ray propagation direction corresponds to the gradient of the phase of your coherent wavefront. What that tells you is that if you have wave that is shaped by an SLM instance, and you place yourself at any location in space, at that location in space, there's only one suitable ray propagation direction. And we know that this is not representative of the light distribution that we're experiencing around us. If we look at scenes with diffuse light, any kind of diffuse light, really, that you take a piece of object, like from any perspective you can see it, that means that from those very, very tiny locations, there is a whole bunch of rays that are being emitted across multiple directions. And so, in essence, coherent light is a very inferior type of light to work with. Another way to realize that coherent holograms exhibit speckle. What is speckle? Speckle is this noise. It's actually, it's not really fair to call it noise, but it's basically this salt and pepper pattern that is very clearly visible anytime you observe a hologram not exactly in the plane where it was rendered. For instance, in 2D, as soon as you propagate it a little bit, you no longer have control over what happens to the light and the mutually coherent, like constructive and destructive interference that may happen. So when you create a hologram in 2D, for instance, above and below this hologram, you realize that light interferes, sometimes constructively, sometimes destructively, and you create those very like unusually like speckle pattern, annoying speckle pattern. And it's the reason why we don't use holograms to render 3D scenes, because speckle pattern is very detectable, very visible, and very annoying to the human eye. But that speckle pattern is indicative of the fact that we're not dealing with three-dimensional distribution of light. We're dealing with two-dimensional distribution of light that we desperately hope to make work in 3 dimensions. So how do we address that? We will address that by playing with time. And so I look back at OpSins and the response time of OpSins reporter. We're looking at this window between 10 and 100 milliseconds. And in that window are all the OpSins we're trying to excite. And that's true. We want to go fast, but do we need to be that fast? The answer is no. The answer is that at time scales that are significantly faster than the response time of the OpSin and the human eye, there are devices that are able to modulate light significantly faster. So I'm looking here at digital micromirror devices, DMDs. They have this flippable mirrors that can be addressed at kilohertz speeds, which is far faster than the speed response time of the biological and the photochemical reaction that we're interested in, like triggering. So we looked into that and saying, like, can play with time as an extra degree of freedom to pattern light. So there's extra space here that we can use and we really wanted to use. And so one of the that we developed, and this is a paper that we just recently published in eLife. It was on bioRxiv a couple of years ago. It stayed very long in the review process, but we finally got it out. We started coming up with ways to sculpt light that play with time as an extra degree of freedom for light sculpting. So the device we have here shoots a laser towards scanning mirrors and uses the scanning mirrors to modulate the angle, the direction of propagation of light, synchronously with the digital micromirror devices that modulates light in the spatial domain. So what we have is we select a particular illumination angle with galvo mirrors, and with a bunch of micromirrors on the DMD, we open and close a digital aperture. And with that, what we can do is really control light in the spatial and angular domain. And what we've been doing is basically modulating the amplitude on the DMD by opening an aperture synchronously with a pair of galvo mirrors that point the light towards a specific direction. And with that, we can create a shifted focal plane, and we can synthesize an illumination pattern that is otherwise difficult to synthesize with coherent holograms. So this is the kind of like 3-dimensional illumination pattern we want. So this is thresholded for visual purposes, but basically we can create those illumination patterns in 3 dimensions, things that are rather difficult to render with a coherent wave. And so my collaborators at Berkeley, now former advisor, and the postdoc issue that developed the application for that, came up with application where basically with CGH, you were sometimes like landing in non-targeted areas. We can customize the function to go around that problem, but with 3D map, that technique we developed, we can simply turn off particular illumination direction if they happen to shoot light towards neurons that we want to avoid. And so the application that he developed is basically a mapping application where we patch a neuron, and we're interested in identifying the neurons that are synaptically connected to that one. And for that, the application that was developed was basically to record the photocurrents being recorded in this neuron as a function of a series of holograms that randomly target voxels in the vicinity of that neuron in an effort to map and identify if there are neurons in the vicinity that are connected to it. So the experiment basically relies on random three-dimensional distribution of photoexcitation. We map the photoexcitation voxels into an array of voxels, and each array of voxels, we run a stimulation experiment, and we record a photocurrent that we basically map into a photocurrent array. And we are looking for basically an optimization model that says, like, can I come up with a distribution of a volumetric distribution X that basically match the predicted measurement of the photocurrent, so that basically my hologram A times the vector X gives me the photocurrent Y. And so this is basically a compressed sensing, where after several recordings, you can start to estimate the volumetric distribution X and basically map this spatially. And what we're able to find basically is a map of the location of neurons that particularly are connected to the one that was being patched. So this was the experiment that was proposed with this technique. And the reason why we feel very excited about this technique is developed that as a one-photon stimulation technique. And so the case that we're really trying to make here is to say that two-photon excitation techniques really suffer from the scalability issue. Like once you start stimulating more than 50 neurons, more than 100 neurons, unless you really work hard on making the best possible holograms and the most sensitive opsin, it appears that there's going to be a cap that depends on how much heat you can really place into brain tissue. This technique was trying to bring back to life one-photon excitation. And the reason why we say bring back to life is that one-photon holographic techniques really suffer from the fact that once you use visible light, your ability to penetrate deep into the brain and to synthesize patterns that will target individual neurons really is affected by scattering and aberrations. And here, we do not have the beautiful single neuron resolution that two-photon holographic microscopes can get, but we get the next best thing, which is that by trading off a little bit of resolution, we're able to get the scalability back, the scalability that you cannot get with two excitation techniques. So this is why we feel kind of excited about thinking again back about what can be done with one-photon techniques. And what we're making a case for here is to say that if you have the ability to synthesize holograms far better with what traditional CGH techniques can get, perhaps it is possible to synthesize holograms that compensate for most of what can be done in terms of like addressing optical aberrations. So in the minutes I have left, we developed the scanless version of this 3D map in my lab, where we basically specify that we want to render an incoherent scene or incoherent distribution of light, and we want to do so by superimposing coherent holograms rapidly in time. An incoherent scene, from our perspective, can be decomposed as a coherent superposition of holograms that are rapidly interleaved in time. And so by doing so, what we do is we come up with an algorithm where we specify an intensity distribution, and we tell the algorithm, say, hey, can you come up with a sum of coherent holograms that will have speckle, so that the sum of these holograms, or their time average contribution, when they add up together, renders the three-dimensional distribution we're trying to get. And if we go fast enough, from the perspective of the user who's going to look at the scene, or from the perspective of the opsin that's going to collect the light, what matters is the time average superposition. The advantage of that technique is that now that we ask our computer to come up with not one pattern, but a distribution of patterns, we scale up dramatically the number of degrees of freedom that we have for hologram synthesis. We will let the algorithm identify how to best distribute the light that we want to, the light distribution that we want to create across those holograms that individually must be coherent wave and individually must be feasible. And simply by adding more frames, we relax the constraint. So we know individual frames are not going to look like the outcome that we create. We know that individual frames are constrained heavily by the fact that they have to be coherent waves. But altogether, all that matters is that they add up to the right result. So by scaling up the number of degrees of control for light sculpting and even though we are working with a technology that's really not great at making holograms, like these are binary modulators, we can come up with techniques that render holograms very well. So this is an example of what we get. Individual frames are optimized for feasibility. There is speckle, but the algorithm can engineer those speckle patterns so that they mutually compensate for each other, so that together the average rendering is Eybposh problem. So in practice, how does that look like? So simply we eliminate a DMD, digital micromirror device. We have a Fourier holography distribution. We specify the target illumination pattern. And here we have our experimental setup where we relay the image to capture the three-dimensional hologram. So we can do experiments and simulations. And this is to give you examples of what we get. So this is coherent CGH with a DMD, terrible holograms, binary modulation. The hologram quality is terrible. And we compared our technique with traditional despeckling method that just simply add a random noise to get rid of speckle. And when you get rid of speckle by adding random noise, you pay for it in terms of contrast. So these techniques have rather poor contrast. By integrating our algorithm that basically try to co-optimize the frames together to render the hologram, we're able to get those rather nice experimental results with an inexpensive technology, with modulators that have like notoriously poor ability to modulate. So we're very excited about that type of technology. And in the 5 minutes I have left, I want to show you something else, which is that we actually came up with a solution that actually synthesizes light field distributions. So a natural three-dimensional scene can be captured with a microlens array placed in front of a camera. The microlens array encodes the ray propagation direction. If you look at the data behind each microlens array, under each microlens, you see the angular domain. You see the ray directions locally, the distribution of how arrays are locally distributed. And we have an image that, for instance, is that cat that is a diffused image. You know that the population of rays behind each microlens is going to be dense. That is, that there are rays across all directions. That is not what you can get with a coherent hologram, where under each microlens, there's typically only one direction allowed. And so we basically came up with a model that basically directly optimized for the light field data. So we took some light field data online for a three-dimensional, and we integrated the light field simulation in our model. If you try to do that with coherent CGH, this is the kind of rendering you get. And you can see here that under each microlens, not very clear here, but there's basically like a sparsity constraint, like the model is desperately trying to only put one ray behind each microlens. But if we let the algorithm populate the domain, the light field domain with just 20 frames here, we can come with something that is pretty well matched to the distribution we want to create. Now, this is a sum of sparsely distributed frames. And when we came up, and actually, I'm not showing the results here, I should. My grad student was showing them on XWest. But basically, we can, since we can match holographic like light field distributions, we can actually match those holographic distributions in 3D. And so we feel very excited about this technique because we are now able to synthesize three-dimensional distributions that coherent holographic techniques do not have access to. And in the 2 minutes I have left, I'd like to thank you all. I'm going to skip the conclusion because we all talked about that. This is the lab. These are the students that developed all this project. We have some funding, so therefore we're recruiting. So if you know anybody who wants to work at the interface between optical technology and neuroscience applications, please let me know. And finally, we have a conference in Boston, SLB 2022, where we're going to be bringing this community together and to discuss those things. And last, in the 1 second I have left, I recently wrote a review paper that is currently in review in neurophotonics about DeepCGH, about dynamic computer-generated holographic techniques specifically applied to optogenetics. So if this is of interest to anyone, please let me know, contact me. I'll send you a copy of what we have. It's currently in review. And if I happen to have neglected a paper or like potentially should be talking about a specific branch that you all have expertise in, I very much welcome your feedback so that I can do them in the revised version and probably send back to the reviewers. So thank you very much for your time, and I'll answer any questions.